Have you ever wondered how those people have designed those puzzle games? No? Well, I have. Now that I've piqued your interest, let me show you something. So, this is the official website from Steven, the guy from Steven's Sausage Roll, and he makes a lot of games. But if you scroll down to his most recent big game, Steven's Sausage Roll, and you click on it, then you won't see any comments. But if you go to archive.org and then you go to his official website at August 8th and you go to Steven's Sausage Roll, he changed the look of his website, then you will see comments. And interestingly enough, comment number 26 asks the following question. After complimenting Steven, it asks, if you read this, Steven, would you mind giving a short insight into your design process for the puzzles? And Steven answers, nah, I don't feel like it. Best as.
Is this what I think it is? Is this a puzzle game conspiracy? A puzzle game conspiracy?
There is only one reasonable thing reasonable journalists do in such a situation. Indeed, they will have to create their own puzzle game in order to prove their conspiracy theory. You're right. I need to write my own puzzle game in order to prove or disprove whether or not there is a puzzle game design conspiracy. So, let me create a new project and call it Trap Puzzler. All right, let's do this. And voila, here we have it, a grid-based puzzle game. Now, how does this puzzle game work? Well, I am this yellow character here, and I can just move him using the left and right arrow keys. So I'm gonna do that. And I can also move those red blocks, as you can see. But I cannot move those gray blocks. If I try to, the entire screen starts to shake. Now, what is the objective of this puzzle game? Well, it's simple. It's just to somehow break out of this constellation of puzzle blocks. Okay. So if you think about it, I can just move this block down here, and then I can come over this side. Now I can push those blocks together, as you can see, to the left. But I cannot, of course, push it beyond that because there are black blocks in the way. Now I push this guy down and I'm free. There you have it, a puzzle game. Quick interlude. In case you yourself have some programming experience, I'd like you to hit the pause button and think about how you yourself would implement such a character movement algorithm. The reason I'm asking you this is because the first time I implemented it, I did a silly mistake, and perhaps you might do the same mistake. So this is how I initially implemented the character movement algorithm. So in case I would be this yellow character and I wanted to move to the left, what I did was I simply moved the character to the left. Now this character landed on a red block, so what I had to do, I simply had to move the red block also to the left. So I shifted the responsibility from the yellow block to the red block. And of course this had to continue until all of those red blocks would not land on other red blocks. And in this case, the operation succeeds and all the blocks move to the left. Now you might already see an issue here. If I try to move to the left again, now if I try to move this character would land on top of a black block. And this would of course not be allowed, so what I had to do is I had to abort the entire operation. So this was my initial approach, so let me quickly write it down. This is the counterexample I've been talking about. So what happens here is if the player wants to move to the left, it pushes first the small block and then the large block, right? But the large block pushes the small block again, And you kind of get into this infinite loop, and then the device just shoots into infinity. Okay, and now you see my past self explaining how to remedy this problem. So first, mark all affected blocks. Right, so we're gonna affect this one. And then, because this wants to move to the left, we also have to move this guy to the left. And because this one wants to move to the left, we also have to move this thing to the left. And now we're done, because this guy already wants to move to the left, right? And since here everything is free, everything is good to go. And then on the second step, you just move all things simultaneously. Whoa. Now, during the creation of this puzzle game, I think I already unearthed the first secret behind this big puzzle game design conspiracy. I think they all use something called a level editor. Now, hear me out on this one. For grid-like puzzle games like this one, it's particularly easy, right? You can just add new blocks like this, right? You can just have this interface where you place blocks on the game, right? And it's so efficient, it's marvelous. So now if I add this black block in here and I restart it, I can see whether or not the puzzle is solvable or not. So now I can just test it, right? And after thinking about it, it seems as though it's unsolvable. I think this is a very big aspect of what they use. Wow, this is incredible. Super efficient. But it's still so difficult to create those levels. I can never create those huge, complicated levels that they use in those puzzle games. How have they done it? This can't be everything. It just cannot just be a level editor. What did they use? Think. What have people told you? What have they said to you? Think.
You need more automation.
Of course. How could I forget? I need more automation. When in doubt, use more automation. What kind of automation can I apply to this? Of course. I can create a solver, because an automatic solver, because if I then try to run the level, I can just press on the solver and it solves it automatically if it's solvable. Wow, that's great, because now I can just say add a red block here, see if it's solvable. No response, it's not solvable. Okay, then I can remove this block and say remove a red block over here. Try again. Of course it's still solvable. Interesting. What if I move this block over here, remove this, add him here? Damn, still works. The level editor does it all, and you don't even have to think about it. I think this is a key step. So mark it down, everybody. Step number 2, a solver. What will we uncover next? Stay with me, everyone. I will solve this puzzle game level design conspiracy. It's time for another interlude, and you already know the question: how would you yourself create such a solver? Press the pause button and we'll see you in just a minute. Is this an interlude inside an interlude? Yes it is, because this time I'm going to ask you how you will make this solver you just came up with even faster. And if you can't, think about why you can't make it faster, because this is exactly going to be the topic that we're going to look at next. While creating your solver, you might have stumbled upon some levels which seem to be more easy to solve. For example, here we have a labyrinth, right? And as you might know, you can solve a labyrinth by always following the right wall. So it's very easy to write a solver for such levels. However, in general, this doesn't really seem to work. Now, a commonly used technique to solve problem A is to simply reduce problem A to another problem B that you already know how to solve easily. Well, in computer science, there are these huge classes of problems that contain similar properties. For example, there's this huge class of NP-hard problems, and if you can solve one problem inside NP-hard efficiently, then you can solve all problems inside NP efficiently. Now, without going into too much detail for what these classes stand for, it is generally assumed that you cannot solve all problems in NP efficiently, and thus you cannot solve problems in NP-hard efficiently. So there is this one problem called 3-set, which is part of the NP-hard problems. It's also part of the NP problem, so it's an NP-complete problem, but that's not so important. What is important is that we are now going to twist this technique of reducing A to B and turn it around. So what we're going to do is we're going to reduce 3-set to the puzzle game. What does this mean? Well, this means if we can solve the trap puzzler game, the puzzle game easily, then we can also solve 3-set easily. However, we assume that we cannot solve 3-set easily, therefore we cannot solve trap puzzler, the puzzle game, easily. Also, as a consequence, we know that the puzzle game therefore has to be an NP hard, thus it's a hard problem. So in the problem of SAT, which is an abbreviation for satisfiability, you're given a sentence and the question of whether or not you can make this sentence true by changing the constituent variables to either true or false. Here, you could change the variables x1 through x4 to either true or false to make the entire sentence true. So in 3-set, the sentence has a very specific structure. Each sentence consists out of sub-sentences which are ANDed or conjugated together. So all of them have to be true. Now each of the sub-sentences itself contain at most 3 literals. Now a literal is either a variable or the negation of the variable. Also, instead of the words and or not, what is usually used are their respective denotations v, hat, bar. Other people use different syntaxes. Anyways, now you know the problem of 3-set, the hard problem of 3-set, and now the only thing that is left to do is to reduce 3-set to the puzzle game Trap Puzzler. This is my construction. So for each variable, I'm going to create one row of red blocks, okay? And the entire thing looks a little bit like this. And the player starts in here. And now the player can go here and he can push the red block either to the right or to the left side. So he will push all these blocks either to the right or to the left side. Now, again, these rows stand for variables, right? And if he pushes it to the right, he will set x1 equal to 1. If he pushes it to the left, he will set x1 equal to 0. And he will have to push it one way or the other, elsewise he won't be able to solve the problem. Now, once he did these configurations, we have to make sure that he won't change the configurations anymore. Thus, we will go into a second state now, after configuring. And then we have checking. So he will only be able to escape if his configuration is a valid configuration. Now here, the blue block, for every conjunct, he will have 3 possibilities to go down through the red rows, right? And now if we have x1, he will only be able to pass through the first blue row if x1 is equal to 1. He will only be able to pass through the second row if x2 is equal to 0, so x2 would have to be pushed to the left, and he will only be able to pass through the blue one if x3 is equal to 1. Great. So the player goes through here, and now he's in this bucket, okay? And now he will have to go back up. Again, he has 3 choices. And now he will only be able to go this way up if x1 is false. He will only be able to go this way up if x2 is false. He will only be able to go this way up if x3 is false. And then he will do this again for the next literal. He will go down again, and then he will go up again for the last literal. And now he will be set free. At least that's the plan. And this is how the realization looks like. So here you can see the player, how he configures the variables one by one. And now he will have to go to the second state. So after configuring, he's not allowed to change any of the configurations anymore. As you can see, he can't go back to the configuration state. Now you can simply just solve the level if it's solvable, and there you go. The puzzle has been solved, and therefore the equation is satisfiable. So for completeness sake, here you can see an example that is not satisfiable. So as you can see, each of the clauses has only 2 literals. So in order to remedy this, each of the third columns has a block of size 3 by 1 in there, which no matter how you set the variable, you won't be able to pass through this one column. So there you have it, a proof that writing a solver is at least as difficult as writing a solver for 3 set, which is assumed to be a very hard problem. Now NP-hardness might sound really bad, right? Why? Well, we might not be able to solve all the levels we care about with a computer. However, the same thing also applies to the human. If a level is difficult to solve on a computer, it's usually also difficult to solve for a human. But that's precisely what we want, right? We want those challenging puzzles for the player. Another thing that I want to point out is this fairly famous paper called Classic Nintendo Games Are Computationally Hard from 2015. In this paper, 4 people proved the NP-hardness for 5 of Nintendo's largest video games: Mario, Donkey Kong, Legend of Zelda, Metroid, and Pokemon. Now, you wouldn't really expect NP-hardness in, say, a platformer like Mario, but still it's there. So this might be an indication that every game should strive to be at least NP-hard, as seemingly all the good Nintendo games are also NP-hard. Now, regardless of its NP-hardness, you will probably have a solver that tries all the possible combinations in one way or the other. So here, for example, we have a search tree. Now, the search tree symbolizes every movement the player could do in each configuration. And as you can see, this tree grows at most by 4 leaves at each level. Now, how big can such a tree grow? Well, it can grow to infinity if you basically just move your character to the right and then to the left and then to the right and so on. And of course, all of these are valid configurations. And after doing this 100 times, you might still find the solution at the end. However, if there exists a solution, you know there also exists a solution with a minimum number of moves. And how do you find this solution on the tree? Well, one way is to do what is called a breadth first search, where you basically start from the top and then you just enumerate through the nodes in a top to bottom fashion. Now, how long does it take to find the optimal solution? Well, if you know that the optimal solution takes n moves to complete, to solve the level, then you know that your breadth first search algorithm will have to look at 4 to the power of n configurations at most. Why? Well, at each level, and you have n such levels until you find the optimal solution, you get 4 more nodes. Thus, finding the entire solution will take at most 4 to the power of n. But this doesn't really help you since you don't actually know n. In fact, the puzzle might not even be solvable and your algorithm just goes on forever and it won't ever find a solution. So what can you do in order, to terminate your program? Well, one thing you can do is you can just stop early and then say, well, I tried it for 40 moves, but I didn't find a solution. And, there's no solution with 40 moves, but there might be one that has more moves. Now, another important trick you can use is called memoization. Now, let's say you're doing this breadth first search and you are in some configuration, and then you move to the right and then you move to the left. Now you're at the same configuration again, right? However, you already discovered this configuration beforehand, so you can basically eliminate this entire subtree in this search tree, since you already saw this one configuration. Now, how do you detect those duplicates during this run? Well, you can just basically make a set, a hash set or a tree set, and then you can just look up whether or not you already saw the current configuration during your search, and if so, you can just ignore it. Now, if you have seen all of the moves, or if you have seen all the configurations that you're currently looking at, then you know that there is no solution, because you already checked each possible configuration. And in most cases, there only is a finite number of configurations, so you ultimately know whether or not there is a solution or not. Oof, that was a mouthful. But I think we're getting closer and closer to uncovering the puzzle game design conspiracy. Okay, write it down. What did they use? They also use a solver, and it seems like all good puzzle games seem to be NP-hard. Well, I mean, all this information is nice, but I still struggle creating actual levels. I'm here, clicking around, trying to make the level nice and stuff, but I just cannot approach their brilliance, So, what else can I do? Think, man, think.
You need more automation.
Of course, how could I forget? When in doubt, one needs more automation. So what is the aspect I'm currently struggling at? Of course, actually creating the levels. So can I just somehow automize making levels? It was at this moment when I realized into what I've gotten myself into. Yes, the puzzle game design conspiracy is real. So buckle up and get ready for some deep analysis. So this is the key idea. You generate a bunch of random levels, then you take the level solver that we previously created, throw it on top of all of those random levels, and sort them according to how difficult it was for the solver to solve these levels. And the most difficult levels that are still solvable are also levels that are very difficult to solve for humans, and thus they make good puzzle games. Now, look at how proud I look to have finally figured this out. Well, if you yourself want to look as proud as I did during this video, I recommend you to quickly hit the pause button and do two things. First, think about how you yourself would create those random puzzle levels, and second, think about how you yourself would rank those levels according to the difficulty of the level. How do you even measure that? So let me first start with the easier part, which in my opinion is ranking the levels according to their difficulty. Why? Well, difficulty really is a subjective measure, right? And what I used is basically a simple heuristic. I just took the number of nodes that it took for the BFS search in the solver to find the minimal solution and multiplied this by the length of the minimal solution, so the number of moves it took in order to solve the level. And then I kind of get a heuristic which takes into account two factors. It takes into account the breadth of the tree, of the search tree, and it also takes into account the length of the search tree or the depth of the search tree. Now, in my opinion, this heuristic gives you a pretty good measure as to which levels are more difficult and which levels are less difficult. Quite surprisingly, just completely randomly generating a ton of 6x6 or 7x7 levels is already, and then ranking them with the solver, is already sufficient to generate quite good levels. However, if you then want to scale this up to 10x10, 11x11, 13x13, you need to do a little bit of tweaking with the generator. Now, one way you can make your generator better is to look at your generator and think about all the parameters you could potentially tweak. So one of those parameters, in my case, were the number of red and the number of black blocks. Now, I can change them to whatever number I want, and clearly, having only 2 black blocks might not really lead to a very complicated 13x13 level. So what you can then do is you can try to figure out which parameters are more optimal than others, and this process is called hyperparameter optimization. Now, for red and black blocks, it turns out that you kind of want to have a 2-to-1 ratio of black and red blocks, and this scales up pretty well to 13, 14, 15x15, and you start to get a lot more reasonable levels, because you eliminated all those levels that are clearly unreasonable. And finally, you can always increase your computational power by using a supercomputer. And if you don't have access to a supercomputer, you can always use Amazon's web services, which are pretty much as cheap as it gets for computational power. So the cool thing about the generator is that it kind of gives you those unpolished ideas for levels, and you have all this entire catalog of ideas. And now you can just import them into your level editor and start to manually change a few things in order to make the level a lot more cleaner or a lot more playable, or you can maybe even make it a bit more difficult by changing a few things here and there. Now again, you can try to take the human element out of the equation by simply doing a nearest neighbor search on the puzzles. So basically what the player does, or the designer, he takes a level, generates it, and then he manually changes a few things. However, you can also optimize this, right? You can take the level you have and then change a few blocks here and there randomly, and discovering the space of all possible neighbors, and try to figure out which neighbors are even better levels according to your heuristics. But in the end, you will need a human that verifies whether the level is a good one, And usually the human always does a better job at, adding those final touches. Now let me show you a small clip of Garry Kasparov doing a certain observation about chess engines, and I also think the same applies to puzzle level generation machines.
And I reached this formulation. A weak human player plus a machine plus a beta process is superior to a very powerful machine alone, but more remarkably, is superior to a strong human player plus machine and an inferior process.
So this is an example of how I would now design a puzzle game. So this is the game here, right? And if I solve it automatically, you can see it's a pretty easy level. However, now let's say I want to just improve the level automatically. So what I do is I just press the button I and I wait. Good, now I have this block, so let me see. Well, it got a little bit more difficult, it had to move this way, but it's still not very hard, right? So let me try that again. So let me undo this and improve again. Ah, now we get this thing, okay. Let me retry it again. Currently it's not set in a way that it tries a lot of times, but now you get quite a difficult level. So now it's far from trivial suddenly. So you can really use this tool to make your levels more difficult over time. Now here's another example that I like to show. So let's say I would remove this block here, right? Or let me actually... So this is the current level, and as you can see it already takes quite some time to solve it. But yeah, so this is the current level, right? Not so easy to solve. Well, what about if we remove this block and instead improve the level and see how difficult the level can be made after removing this block? Now this will take some time because it's a larger level, so generating or improving the level takes more time, and I'm just running this on a single computer and not on a supercomputer. But here we go. So it seems as though they placed the same block, but they shifted the position of the block a little bit to the right. So let's see how difficult it is to solve the level now. So I pressed on L, and there you can see it has to kind of do this additional step of pushing the block to the left. So I didn't really have to do anything, I just had to press on the improve button and I immediately got a better level. So this is how you optimize level design, in my opinion. And there you have it. This is how I believe Steven and all those other puzzle designers created their puzzle games. Now, is it a conspiracy? Probably not. Anyways, if you want to try Trap Puzzler out yourself, link is in the description. There are 9 difficult levels for you to solve, well, with increasing difficulty. And there's even a final boss at the end. And also, the level editor is also included. So in case you want to try out the solver and the improvement generator, link is in the description.
You are amazing.